Okay, so here's a video about where I think we're going with this project. Um, Basically, things are working in lab right now, and I wasn't quite sure what was going to be possible, but I think what I'm about to propose should be easily doable so that we can do a great senior project. And actually, there might even be more than one paper in what we're doing here. So the paper in question is we're going to do compact modeling of hafnium oxide silicon carbide MOS devices. And a compact model is really a SPICE model, right? So we're going to present the extraction of an EKV SPICE model using TCAD and compare it to as-grown MOS devices. Or and another way of saying that, though, is we're going to calibrate the TCAD model with MOS capacitor data. All right. So the way the flow would work is that we take the high frequency CV curve using the mercury probe, right, for a MOS structure, and we can extract the substrate doping, fixed oxide charge, threshold voltage, flat band, gamma, phi, can all be calculated, right? Then that can be used to calibrate a TCAD MOS model to where now you know that the TCAD is matching reality. Now, of course, you can start with the TCAD model, make sure everything is working, and then put in the constants of the things that we just measured, right? Then you take that MOS capacitor and effectively add two diodes to it and turn it into a MOSFET. And then you can, and so while it's not calibrated against a transistor, the MOS part is calibrated against a real device. So then an EKV SPICE model can be extracted from that silicon carbide TCAD model, right? And then that SPICE deck can be used to design an op-amp using the GME over ID technique. All right, and so even though this is the flow, a lot of this I know we've already done, and we just need some measurement data to then calibrate it. All right. The wafers should be here any day, or they should ship any day. Well, it is what it is. But in the meantime, you have to calibrate your process anyway. So we started with silicon wafers, and we have some preliminary results there. But I also have gallium arsenide and indium phosphide substrates that we can explore. Now, gallium arsenide and indium phosphide do not make a they don't have a native oxide that's as useful and reliable and robust as silicon dioxide, but we can deposit hafnium oxide on those other substrates to make TCAD models for those material systems. All right. Now, part of that is you want we need the analytical equations for the things that we're extracting as well, right? That's the theory part. But here's the things that we can do, right? We can extract, so everything that we kind of said up here, right, we can do for silicon dioxide silicon MOS, hafnium oxide silicon MOS, hafnium oxide indium phosphide, same thing for gallium arsenide. And then once the wafers come, we can grow silicon dioxide silicon carbide MOS, and then ultimately hafnium oxide silicon carbide MOS. And yeah, there's probably more than one paper in there, but we basically just have to start doing things that are possible. And it's a pandemic, and you know, the supply chain, I don't think our wafers are stuck in the Suez Canal, but you know, they're stuck somewhere. So anyway, here's the silicon dioxide, right? And I've even started to write the the procedure, right? Standard SE1, SE2 cleaning process. Prepare these kind of wafers. I have to find out how long they were grown under what conditions, wet and dry, or we just do it again, right? And the thickness was measured with a UV capable spectrophotometer to be 335 angstroms with a standard deviation of, and I have to look that up, CV measurements were carried out at 23 degrees C at a frequency of 2 megahertz. And then here's the actual thing. Now with this data right here, right, with the substrate doping, fixed oxide charge, right, and the oxide thickness, and the fact that the top gate is mercury, Adam, you could now go make a TCAD model to try to get that same curve, right? Now, just so you know, this link, the picture is linked, right, to the actual raw data, right? And what can be done is in the TCAD model, export the CV curve and then scale the two areas of the measured and the simulated, and then put them in one Python plot, right? And that would make, you know, an excellent figure, right? Now, this part wouldn't come out, and we would have to then kind of write it out by hand later in the text, all right? So that's where we're at with that right now. If you want to see, we're trying to develop a Mercury Pro baseline process so that it's like a lab manual for doing what we're doing, right? And this final figure, which it's good for us, but probably not to be put in the picture, is it calculates a theoretical model based on the measurement data. So in a way, this is doing what we're going to do with TCAD, right? But you just calibrate it to make sure that it works, all right? And this doesn't have like a silicon carbide option, if you will. Okay? But that's pretty much it. I thought I'd just